We're starting Year 13 course with Topic 1 on circular motion, which looks at objects being pulled into a circular path by a force that acts towards the centre, what's known as a centripetal force. Now, this is different from linear motion, where an object travelling in a straight line might have constant velocity. Because velocity is a vector, anything travelling in a circle has constantly changing velocity because it's constantly changing direction. So therefore, it needs other equations in order to calculate what's happening. I've included the specification, so if you wanted to pause and look at that, feel free. And today we're looking at the first 4 points of the specification, starting with the period of rotation and the frequency. We'll move on to look at a new unit, which is radians, which links to the angles that an object's turning through. And we'll go on to look at angular velocity. So to start with, we're going to consider what is circular motion. As I mentioned, it's any object being pulled into a circular path. So you can see on the left, the heavy object's being pulled into that circular path by the force of the cable in the person's hands and connected to that object. Then on the diagram on the right, you can see it includes a blue arrow. That is the instantaneous velocity at any given moment. And you can see that is constantly changing as it moves around the path. Now, if that force was removed, that blue arrow gives an indication of where the object would go once the force stopped acting and pulling it into a circle. Our first two key terms then, frequency is obviously going to be a familiar term, having covered it at GCSE and earlier in the course. So frequency, denoted as F, need to remember is measured in hertz, can have prefixes as well, and is abbreviated to Hz. Now, when we were covering this at GCSE, we'd have learnt this in terms of waves, and whenever we're dealing with frequency, it's always the number of something per second. And in this particular case, because we're dealing with circular motion, it is the number of rotations per second. The period of rotation is the inverse of the frequency. So it's how long one rotation takes. So because it's the inverse, we can literally flip these two terms around. So it's denoted as a capital T. Because the unit for frequency is technically per second, the units of the period is just seconds. And our definition for this would be the seconds, or the time taken to complete one rotation. So it's seconds per rotation. To give an example of that, we're going to consider a smooth motion clock. It's not a ticking quartz clock. And we can look at the second hand. Now, obviously, the second hand would take a full 60 seconds to complete one rotation, 1 minute. So the period of rotation for a second hand would be 60 seconds. The frequency is obviously not going round that often. So the frequency is actually very low. And the frequency is, in fact, 1/60, because these two things are the inverse of each other. So 1/60, very small number of 0.016 recurring, and that would be in hertz. Okay, and because of that, we build a relationship where the period is equal to 1/f, which can obviously be written the other way around, where f is equal to 1/the period. And you need to be familiar with that relationship in order to convert from one to the other quite easily. Moving on to point B of the specification, and that's introducing this new idea of the radian as a different way of measuring angles. Now, we're familiar with measuring angles in terms of degrees, but for this unit, we need to be measuring angles in a new unit, radian. So we need to know the definition of the radian, which I've put in the box for the Word version, and linking that to an equation. So any amount of radians can be calculated by dividing the arc length by the radius of that circle. So for 1 radian, that is when the arc length would be equal to the radius. So no matter what two values these are, they would give an answer of 1. So when this distance here which is the arc, is equal to the radius, we know that this angle would be 1 radian. Applying that to a complete circle, so any object that does one complete loop will have turned through an angle of 360 degrees. And we're very familiar with working in those degrees, but we need to be able to do that in terms of radians. So we use that equation of the radians being equal to the arc length divided by the radius. Now the arc length for a complete circle would be equal to the circumference. So applying that idea, we end up with a circumference divided by the radius. And that circumference is equal to pi d. We end up with pi d over r. That diameter is twice the radius, so that is the same as 2 pi r over r, which gives a final answer of 2 pi. And that is a key fact for this unit. So as radians is probably a new unit for most of you, I think it's important to get used to moving between radians and the more traditional degrees. So I've included a task sheet in the assignment for you to try, doing both those, converting from radians into degrees and degrees into radians. Now, it's a fairly simple process if you compare degrees to radians and think about how you can move between the two. So if we once again consider a full circle, which would be 360 degrees, and that is the equivalent of 2 pi radians. So to move from one to the other, we're going to ignore the pi and just think about how we can generate the two. So moving from degrees to radians, the first thing we're going to do is divide by 180 degrees, and then we need to multiply by pi to generate that pi. So 360 divided by 180 would give you the 2, then multiply by pi would give you the pi. And obviously going the other way would be the opposite. We're going to divide by pi and multiply by 180. So using that, that should make that worksheet fairly straightforward. And I will post all the solutions to that worksheet when I post lesson 2, so you can check your own work. We're going to bypass point C for the time being because it's just an application of B, looking at radians and using radians in questions. So as you practice the exercises and past paper questions, you'll be learning point C as you go. Point D is looking at angular velocity, so the velocity of an object as it moves in a circle, and how that links to our previous terms of frequency and period for circular motion. So if we consider, again, an object moving in a circle and it travels along that arc, so it's covering a distance of that arc, which we're denoting as S. So it's now turning through an angle theta, and the circle traditionally has that radius r. So by applying speed equals distance over time, we can generate this first equation. Speed as it moves along the arc is equal to the distance it's travelled divided by how long it took. But linking that to our definition of the radian, where the number of radians is equal to the arc length divided by the radius, if we rearrange that for S, we get S equals theta times r, and we can substitute that in for S. So we get that the speed as the object moves along that arc is equal to the radius of the circle multiplied by the number of radians divided by the time it took to move along the arc. Because that radius is now constant for the circle, it no longer impacts the velocity, the speed of that object. So the speed of the object is now proportional to this ratio, the radians divided by the time. And that's how we define angular velocity. So our angular velocity is equal to theta, the number of radians, divided by the time. And we can define theta then as the rate of change of radians. Okay, so two important parts there. In an equation, theta, which is a Greek letter, like a curly W, is equal to the number of radians divided by the time, and our definition, rate of change of radians. Now there is a more complex definition, more traditional definition at the bottom in the box, but this is a perfectly acceptable definition to use in exams. And the final part we're going to look at on this slide is actually completing this equation. So if we now know that theta over t is equal to omega, we can finish this equation by substituting in omega. So V equals R multiplied by omega, or it is more traditionally written, V equals omega R. And that is one of the equations that will be in the booklet for exams and supplied, but you do need to know how it came about and be able to use it. So, final part for this lesson is linking this angular velocity to frequency and period. And we're going to look at that for one complete circle. And we're combining the idea of an object traveling in one complete circle with our definition of angular velocity. So omega is equal to theta, the number of radians, divided by the time. Now, if we're traveling in one complete circle, that means that theta will be equal to 2 pi. And from our definition of how long it takes to complete one full circle, t, or lowercase t, becomes capital T, the period. So that is our first equation that links various features of this topic, that the angular velocity equals 2 pi divided by the period, the time taken to complete one full rotation. However, earlier we looked at the fact that t is equal to 1 over f, and we can substitute that into this equation, which give us 2 pi over 1 over f, which simplifying becomes omega equals 2 pi f. Now, obviously, we can rearrange those two equations. This first one could rearrange for the period being 2 pi over omega. And we could rearrange this one for frequency being omega over 2 pi. And once again, this embraces the fact that the period and the frequency are the inverse of each other, because the right-hand side of these two equations are the fractions flipped upside down when you compare them. Okay, so again, that shows that the period is equal to 1 over f. So I've included this to summarize the key terms we've covered today on circular motion. And to round this off, I've included a second task for you. It's quite a large task. There's 40 marks available for this and gives you practice of using the equations. So just to summarize those as well, you need to remember that the period is 1 over f. The angular velocity is equal to the number of radians divided by the time taken. We can also say that the speed is the angular velocity multiplied by the radius. And by linking these first two, we could say that the angular velocity is 2 pi over t, which is the same as 2 pi multiplied by f. Okay, so using those equations in this task, let me know if you have any problems.